moments. You're making a big deal out of it. It's not a big deal. Suppose I had this following data. 4 people have a race, and one person crosses the finish line in 1 minute, and 2 people cross the finish line in 2 minutes, and another single person crossed the finish line in 3 minutes. What is the average time for running the race? Okay, so here's the numbers. Here's the numbers. We can plot the numbers. If you don't like arithmetic, look at the numbers. Look at the plot. It's not hard to figure out what the average time is. But if you had a lot of numbers, you wouldn't be able to tell. And you would calculate the average time by the number of runners multiplied by the time each runner took to cross the finish line, divided by the total number of runners, which is the sum of the number of runners at a given time. And that's going to work out to be 1 runner times 1 minute, 2 runners times 2 minutes, and 1 runner times 3 minutes. And obviously we have a total of 4 runners. 1 plus 4 plus 3 is 8. 8 divided by 4 is 2 minutes. That's the average time. Now, suppose instead of the table being time and numbers of runners, it was the number of molecules coming out of the end of a column. Well, we'd have more than 1, 2, and 1, right? We'd have numbers on the scale of Avogadro's number. But it's the same calculation. And we could replace the number of molecules with a fraction of the total molecules that are taking a certain amount of time to move a certain distance. It would be the same result. The calculations in all cases would be something related to the number of molecules or the fraction of the molecules times the time divided by the total number of molecules, or if you were summing up the fractions, the sum of all the fractions would obviously work out to be 1. Okay? This is simply the average time. It's the first moment of the distribution of running times. That's it. It's the same as any average. The second moment is the same exact principle, except instead of being the time to the first power, it would be the time to the second power. And the standard deviation of the distribution would be the time minus the average time squared. That would make it the second moment about the average, the second moment about the mean, the second moment about the center of gravity, the center of mass, whatever you want to call it, of whatever distribution you're talking about. That's all the moments are. And when you take statistics, elementary statistics, they only tell you about the first 2 moments. But you can have any moment you want. You can have the 3rd moment, the 4th moment, the 5th moment, the 6th moment. They all have different physical and mathematical interpretations. If you get into polymers, synthetic polymers, we talk about the number average molecular weight, and we talked about the mass average molecular weight. And those are simply different moments of the distribution of molecular weights of the molecules. One is based on the number of molecules, and the other is based upon the fraction of the mass of a molecule of a particular molecular weight. It's the same thing. There's really not, just because we call it a moment doesn't make it any different than the statistical concepts. Now, if you've got a very large number of events, you get a continuous curve, not a discontinuous curve. And so now, instead of doing a summation in the limit of a large sum of closely spaced things, we can replace the sum with the integral. And if we have a continuous distribution, like a Gaussian distribution, or a Poisson distribution, or an exponential distribution, we replace the summation with an integral. That's all there is to it. And we represent the stuff coming out of the end of the column as a continuous distribution, except when we got a plate model and we got small numbers of plates, then we have to deal with a discontinuous distribution, and the integral wouldn't work so well. You'd have to do the actual calculation, which is what we did back when we were playing with the plate model. So that's what moments are all about. Now, it turns out that for a perfectly Gaussian distribution, the first moment is, if it was the distribution versus time, the first moment would be the retention time. If it were a distribution versus volume, then the first moment would be the retention volume. The second central moment is simply the sigma squared of the Gaussian peak. That's the characteristic of the Gaussian peak. And if it were a distribution versus time, then sigma squared would have time units, so it would be seconds squared or minutes squared. If it were distribution versus volume, then the sigma would be in volume units, milliliters or liters or microliters or squared. So that would be seconds squared or milliliters squared. And that's basically it. Now, if we have a non-Gaussian distribution, which is what we get if we put into a chromatographic column a rectangular pulse of solute, if you put in too much, the distribution becomes non-Gaussian. And I gave you the moments of that distribution the other day, and I think they're in here somewhere. Yes. This is the 0th moment, which is the area. It's equivalent to the total number of runners. This is the first moment, which in volume units would be equal to the retention volume of the Gaussian plus the 1/2 of the sample volume, assuming a rectangular pulse. If it was some other function, not a rectangular pulse, but a triangle, or well, it could actually, you could, if you wanted to, model the input distribution as another Gaussian, then it would be the sigma of the other Gaussian. I'm sorry, it would be related to the sigma of the other Gaussian. And then the second central moment is the sigma squared of the Gaussian plus the injected volume squared divided by 12. Again, the 12 applies only to a rectangular pulse input type distribution. And if we wanted to, we could calculate a 3rd moment, a 4th moment, a 5th moment. You can calculate as many moments as you want once you have the function. You just stick it in the right integral, and out comes the answer. And we talked about that, and we got into the RC filter. This is the response of a, meaning a very, 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 very narrow rectangular pulse. And It follows a negative exponential versus time, where it has a characteristic time tau called the time constant of the filter. Electronically speaking, tau would be equal to the RC product. If you put in R in ohms and C in farads and work it all out, R times C has units of seconds in SI units. And I went through these with you the other day. And then I showed the impact of that time constant on resolution of two pairs of peaks. And the importance of this slide is that these two earlier peaks are more impacted by the time constant than are these two later peaks. And the reason that is so is that these peaks inherently have smaller sigma values. The early peaks have smaller sigma values than do the later peaks. So the ratio of tau, the time constant of the filter, it's the same filter for all the peaks. The ratio of tau to the sigma is greater for these early peaks than it is for the later peaks. So the resolution of the early peaks is more messed up than the resolution of the later peaks. And this is the influence of the tau to sigma ratio on the ratio of the height of the peak with a zero time, whatever the time constant is affects this, and this is with a zero time constant. And you see, if tau over sigma is really small, then h over h naught is 1, and the peak is at its maximum height. But as you turn up the time constant of the filter, the height of the peak comes down and down and down and down and down. The area is the area is the area. So if the height comes down and the area is constant, then the peak has to get wider to maintain that area. The peak maximum will shift as you increase tau relative to sigma. So this is the difference between the position of the peak. So this is the peak apex, okay, the top of the peak. And this is the true retention time if you had a zero time constant relative to sigma. And you see that it shifts, the peak shifts out and out and out and out and out as you increase the time constant. And that's bad too, because now you don't really know where the peak is. If you were looking for a peak at a retention time of 10.12 seconds and your time constant is too high, it's going to come out at a time of maybe even 11 seconds, which would be bad news. You'd say, oh, that's not my compound. And this is, if you thought the previous one was bad, this one's worse. It's just the way the arithmetic works out. This is the so-called exponentially modified Gaussian peak function. There's nothing in here that you can't get Excel to do. It's just two ERF functions and then an exponential function. So all of the graphs I showed you were computed with this function written in Excel. But don't worry about it. But what you need to worry about are the moments of the exponentially modified Gaussian. I'm not giving you the equation for the peak area because the filter has no influence on the peak area. The peak area is the peak area is the peak area. The reason why I gave you an equation for the zeroth moment for the rectangular pulse is if you put more sample in, the area has got to get bigger and bigger and bigger. So you need that one. But this is, whatever the area is, it is. The first moment, the center of gravity of the distribution will be equal to the retention time of the pure Gaussian. That is, if there was zero time constant, TR would be the maximum point in that distribution. But if you got a time constant, the first moment, the center of gravity, which divides the area in exactly halves, occurs at this plus tau, the time constant of the filter. The second moment is equal to sigma squared of the Gaussian plus the time constant squared. Comparing this to the result for the rectangular pulse, the rectangular pulse was TR plus V star over 2, and this was sigma squared plus V star squared over 12. Squared, squared, first power, first power. The 2 and the 12 come from the difference in the geometry of a rectangular pulse versus an exponential decay. That they just result from the appropriate integrations. This you gotta know. Okay, now suppose you have a peak which is tail. And how do you calculate a plate count? Well, you got a problem, because this equation, n equal to VR divided by peak half width squared times 2.354 squared, or 5.54 times this squared, only works for a Gaussian peak. This was derived assuming that the peak was Gaussian. But here's a typical exponentially modified Gaussian peak. And these two guys, John Dorsey and Rob Foley, came up with a really slick way of graphically, without a whole lot of messing around, a way to find out what the true value of the Gaussian contribution is and what the true value of the plate count is. Okay? And what they recommend is that you measure the width of the peak not at the half height. The half height is there. They say measure it at the 10% of the total height. So this is the 0.1 width. So you measure the width of the peak by finding this time and this time, subtract one from the other. That gives you the width of the peak. That's one thing you have to do. The other thing you have to do is measure B and A. And what you do is you take, you drop a vertical from the peak maximum. So you go to the peak apex and then drop a vertical to the baseline. B is the distance from the dropped vertical over to TB. A is the distance from the dropped vertical back to point TA, the 10% height point. So we need the sum and we need the ratio of B to A. And doing a lot of algebra and a lot of curve fitting, they came up with the following results. They say that the plate count is best calculated by taking the ratio of VR to the width at the 10% height squared, multiply that by 41.7, and then you have to correct for the asymmetry of the peak, and this will give you the plate count of the whole tail peak. If you were to take this tail peak and apply the Gaussian formula to it, you would get a number that is really different from this number, depending upon the degree of peak asymmetry. Okay, if the peak was really asymmetric, this number could be quite different than what you'd get by saying the peak is Gaussian. The other thing is, if you want to get the retention time of the real Gaussian peak, that you get from measuring the time of the peak apex, and then you apply this correction factor. This second one is not very important. This is the one that we use a lot to get a decent plate count when we've got a tailed peak. Now, most of the chromatographic data systems on this planet assume that the peak is Gaussian. Doesn't matter if your eyeball is telling you that's not Gaussian. It assumes it's Gaussian unless you override some of the algorithms in it. If you don't override the algorithms, it's going to measure the half width of the peak. It's going to pop that into the Gaussian formula that I just showed you on the previous slide, and you're going to get a plate count. And it's going to be wrong. Okay? However, I also don't know of any data systems that you cannot override the default algorithm and tell it how, it'll give you a number of options as to how it would evaluate the true plate count. And one of them could well be assume that it's an exponentially modified Gaussian, and then it's going to implement something like what I just told you about. Another option that you can pick on most data systems is you can say, oh, just calculate the peak moments. That's all I care about. Just give me the first moment and the second moment, or the second central moment, and I'll calculate my plate counts myself. You can do that. Those default, they're not defaults. You have to go in and consciously make it happen that way. Okay, that's the end of extra column broadening. And I'm going to change gears now to something which is very important. And that's what happens when the chromatography is done with a nonlinear isotherm. This is, in general, this is an extremely difficult subject. We're not going to get into the mathematics of it at all. There's a just wonderful book by George Guichon on preparative chromatography. It's called Prep Scale Liquid Chromatography. It's about yay thick. It's close to 900 pages. It's a wonderful book. If you get into prep scale chromatography, you've got to have that book. I'm going to give you not what's in that book, but just enough to be dangerous. If I have time, I'll talk about this first subject. I'll talk about this if I finish on time here. But what we're going to talk about is the effect of nonlinear isotherms on the position of the peak, on the shape of the peak, and on the width of the peak. And there is nothing pleasant about this. There is no good. There's bad and there's ugly. This should be called How to Make an Ugly Peak. Okay. What we've been talking about so far is what's called a linear isotherm situation. And in the linear isotherm, the concentration of the stuff in the stationary phase at equilibrium is linearly related to the concentration of the stuff in the mobile phase. That's down here. What I mean is it's a straight line and it goes through the origin 0, 0. We've written K equals concentration in the stationary phase over concentration in the mobile phase a lot. This is a plot of that equation. And a Gaussian isotherm, excuse me, a linear isotherm results if you have enough plates. 100, 200 plates, according to the plate model, is more than adequate to give you a Gaussian peak. Gives you a Gaussian peak, nice and symmetric. And we've learned also that the retention volume or the retention time is independent of the amount of stuff injected. The peak doesn't move if you increase the concentration that you inject. Doesn't move. The concentration that you inject. We're talking here always now about a small volume. So we're not convolving together two different processes. There's the process of volume overload when you inject an excess of volume into a small column. We're talking about mass overload when there's no more room left in the stationary phase for the solute to behave in a linear region. Now, there's two kinds of deviations from linearity. There's negative deviations, like I've drawn here, where it goes up and then curves over and flattens out. That's called convex curvature, negative curvature. And because it looks a lot like a particular isotherm called the Langmuir isotherm, after Irving Langmuir, it curves like that. Now, if you actually inject enough stuff into the column so that you get into the nonlinear part of the curve, the resulting chromatographic peak will not be Gaussian. In the case of this kind of isotherm, the peak is going to be tailed. By tailed, I mean that the long time edge of the peak, this is as time goes that way, the long time edge takes a long time to get back down to the baseline. That's a tailed peak. What you will find in this instance is that the retention time, if you inject a lot of stuff, the retention time, the position of the peak maximum, is going to drop. So this is your retention time here, and inject a little bit of stuff, it's constant, but you can inject too much and it starts to come down, and the more you inject, the more that peak moves in, until eventually it'll move into the dead time of the column. There's a second kind of isotherm. It's where the curvature goes the other way, and this is what's called concave or positive curvature, and it's also called anti-Langmuir. And that sort of tells you anti-Langmuir behaves exactly anti what a Langmuir does. So, if you inject too much stuff, instead of having a tail, you have a front. And the front eventually can extend all the way into the dead time of the column. And the peak maximum moves out and out and out and out and out, and there's no limit to how far out it can go, theoretically. The retention time, instead of dropping off as you inject more stuff, the retention time can shift to more positive numbers, to greater numbers, as more sample is loaded into the column. Now, the question has to arise, why the heck does this happen? Why is this simple and either of these so bloody complicated? And the answer is it has to do with the nonlinearity of the phenomenon. I'll get there in a minute. This is an actual model that shows you what happens in the case of a Langmuir type isotherm. This is named after two other people who came up with a very simple model that has the same kind of curvature as a Langmuir curvature. So this is a negative or convex isotherm, or a Langmuir-like isotherm. It's not exactly Langmuir. They made it simpler so they could do some integrations that were very difficult to do with the Langmuir. But you can see what happens. We inject a little bit of stuff, nice Gaussian looking peak. We inject more stuff and bang, that peak is moving in. And if I keep injecting stuff, the peak keeps moving in. And it's obvious that the half width of this peak is a lot wider than the half width of that peak. And when we look at the peak now, there's a big long tail. And it's not an accident that this curve overlaps the one on top of it, and that overlaps that one, and that overlaps that one. This is a physically required consequence of the nature of the convex isotherm. This is what happens in reality. Some people call this a shark fin peak, for obvious reasons. I can't flip this over and show you, but in the day of transparencies I could. If I had a concave isotherm, an anti-Langmuir isotherm, I could take this and rotate it 180 degrees and show you what a fronted peak looks like. So imagine rotating this around the maximum, and that's what a fronted peak looks like. See, if I rotate this, it doesn't help. Okay, so why does this happen? Well, let's think about a linear isotherm. Beta is the K factor for the isotherm. It's the ratio of the concentration of the stuff in the stationary phase to the concentration of stuff in the mobile phase. This beta is bigger than that beta. The velocity of the solute zone is equal to the velocity of propagation of the mobile phase, which I can call u sub 0, divided by 1 plus k prime. And k prime would be equal to beta times the phase ratio. Now, which of these two zones, the one corresponding to beta 1 or the one corresponding to beta 2, is going to move through the column faster? The one with the smaller k factor, right? That's going to be beta 1. Okay, so as I increase the k factor by whatever amount, as I increase the k factor, the zone moves slower. Okay? Now, it doesn't matter if I inject this much, this much, this much, or that much. The slope is the same everywhere because it's a linear plot. So the beta is the same everywhere. So the velocity of the zone is the same here, 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 and here. Now, suppose I have a convex isotherm. If I inject a very small amount of material, I probably remain on this linear isotherm. And I'm not going to see anything happen to my peak. But let's suppose I inject this much stuff. I'm now on to the part of the isotherm where it started to curve. The average slope would be taken from the origin and where it crosses through this point on the true isotherm. And I say that that average slope corresponds to a certain beta. I'll call that beta 2. Now let me inject more. Suppose I inject this much out here, and I again determine an average slope, and I'll say that that corresponds to a beta 3 at this really high concentration. Now the solute at concentrations below beta 1, this point 1 on the curve, they're all moving with the same beta. Nothing bothers them. They're behaving linearly. But some of the molecules here have to behave as if beta is smaller. Now if beta is smaller, the K factor is smaller, and some of those molecules are moving faster than the other molecules which are in a more dilute region of the column. So what I'm telling you is that the velocity of the molecules depends upon what concentration they're at. So, instead of drawing Gaussian peaks, I'm going to do a triangle peak. These molecules at high concentration, I know that it's up at the top of the peak, they're into the region of beta 3. Beta 3 is smaller than beta 2, which is smaller than beta 1. So stuff in the beta 3 region is moving at a higher velocity than stuff in the beta 2 region, which is moving at a higher velocity yet than the stuff in the beta 1 region. So these molecules here are moving fast. So I give them a long vector, meaning a high velocity. These molecules have a shorter vector because they're not moving as fast, and so on. So now, imagine that you're in this peak, and you're at the top of the peak. You're moving forward rapidly. The guys lower down on the peak aren't moving as fast as you're moving. What's going to happen is that this front is gradually going to become vertical. It's going to look like that. So the peak now looks like this inside the column. Now, let's put a detector right there. There's our detector. What's it see? It sees, whoa, there's a really sharp front, and then long tail. So all the stuff I just told you about back on that first slide is a consequence of the fact that the molecules move with different velocities. And that's it. Wasn't that fun? If you think about it, why does an incoming surf form a wave with a sharp front and a long tail? It's the same phenomenon. The water, which is close to the bottom of the beach, experiences more drag because it's closer to the bottom of the beach and it moves slower. But the water further up in the water column doesn't have as much drag. And so it starts to move faster than the water at the bottom of the water column, and eventually you build up a front out of bottom.
So in the column then, since you have surface like around the whole thing, does that mean the middle moves fastest and then the outsides are dragged back?
No, we're not worrying about a radial distribution in the column, and you took my analogy to friction much too seriously. It's due to the nature of it's due to the isotherm. The isotherm curvature plays the role of either positive friction or negative friction, but it's not friction. It just impacts because the velocity is given by that equation, and this is varying with the concentration, the local concentration, meaning the concentration on the z-axis of the column is varying. So this is varying, so that is varying. Okay, it's not due to wall friction with the column at all. There are effects, but we're not worrying about them now, and they're much smaller than these effects. Okay, now I did finish. I sent you yesterday an email, and attached to that email was this, can't write on it. I've sent you an Excel spreadsheet called HPLC Simulator, and I also sent you a Word file, which is a work that tells you what to do. Let me open up the Excel. Oh, come on. This is impossible to do at this point in time. I'm going to have to use another computer to show this. I did this the other day and I didn't have to sign in.
Was it on the other computer?
They wanted you to update Excel,
Yeah.
and so it went online to go update it.
Oh. Well, I'll take care of that some other time. In any case, let me tell you what this is about. There is a spreadsheet which does a really good job of simulating a real HPLC system. You can change anything you want to change. You can change the mobile phase composition, the temperature, the flow rate, the particle size, the length of the column. You can change whether it's a good column or a bad column in terms of plate counts, and it takes care of all that stuff. And there's like 20 or 30 different molecules with different chromatographic properties. And I've given you a 5-component mixture that you have to figure out how to separate by choosing the right parameters. And then I have a number of tasks which I want you to do. I want you to look at the effect of the amount of sample injected, the volume of sample injected, the effect of the time constant on the detector, the effect of particle size, and the size of the column, whether it's a 4.6 millimeter diameter column or a 2.1 millimeter diameter column, which are the most popular column diameters to use, and see what the consequences of that are on the separation and on the characteristics of the piece. And so there's a list of, I think, 10 or 11 tasks. It's more or less the equivalent of going in the lab and doing it yourself. I guarantee you that the results will be within 5 or 10% of what you would do on a good column in a lab with those molecules. And then I want you to write a report on what you observe. If you want to do this with a friend, that's perfectly all right, or 3 friends, or 8 friends, I don't care. But each report will be written by one person and I'm going to evaluate the reports. And then after I evaluate the reports, everybody in the class will come to see me for 15 minutes or so, and then explain to me what you observed and answer some questions that I'll throw at you during that 15 minutes or so. This is a significant chunk of your grade. It's not 50% of your grade, but there'll be a couple of assignments like this, and they will add up to a significant chunk of grade. So this is a serious thing. You want to get started now, even though that you won't understand some of the LC stuff right now. There's a bunch of things that you have the background now to understand, and you may as well start now rather than 2 weeks from now when you understand everything, and leaving you less time to get it done. So start now. In the Word file, I've highlighted in yellow the stuff that I believe you should be able to understand now. So don't worry too much about the stuff that's not highlighted in yellow. You'll get that later, okay? The nature of this material is we start here, we do this, 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 where you want, we go deeper, deeper, deeper. That's the nature of the material. But I think when you finish, when you know this stuff that is in yellow, you may as well start on it now rather than a couple of weeks from now. I think it's actually a lot of fun to play with it to see what you can do. I believe when I left it such that you're only going to see 2 peaks. So, but there are 5. All right, there are 5. Also, probably a good idea to make yourself 2 copies of it, because at some point you're going to screw up one of the cells that I tell you don't do anything to this cell. Anything in yellow in the Excel is a computed parameter. Don't change it.